Imagine you're on a spacewalk and the safety tether suddenly slips from your grip. You are drifting away from the station, completely exposed to the vacuum of space without a pressure suit. If you trust the movies, you might think your blood would instantly freeze into solid ice, or worse, that you'd explode like a balloon. The actual biological reality is much stranger and far more gruesome than anything you've seen on screen. From the moment you are exposed to the void, you have exactly 90 seconds to survive. The total absence of atmospheric pressure is your most immediate enemy, acting on your body far faster than the extreme cold. In those first few seconds, your human instinct will scream at you to take a deep breath and hold it, and doing that is a fatal mistake. This diagram shows what happens inside your chest. With zero pressure outside your body, the air trapped inside your lungs will rapidly expand. If you keep your mouth shut, that expanding volume will literally tear and shred the delicate tissue of your lungs. It is the exact same physics seen in NASA's high-altitude weather balloons. As atmospheric pressure drops, the trapped gas inside swells dramatically. To survive your first 5 seconds in a vacuum, you must do the hardest thing imaginable: violently exhale every ounce of oxygen in your lungs. This graph maps atmospheric pressure against the boiling point of water, illustrating a precise threshold known as the Armstrong limit. As pressure approaches zero, the temperature required to boil a liquid plummets, dropping perfectly in line with 37 degrees Celsius, your normal body temperature. This triggers a medical phenomenon called ebullism. Without external pressure to hold liquids together, the moisture on your tongue, your tears, and the water inside your blood plasma begin to spontaneously boil. As those vapor bubbles form and expand rapidly, your body will swell to nearly twice its normal size, a reaction heavily documented in extreme vacuum chamber testing. But you won't pop. Human skin is highly elastic, making it strong enough to contain the swelling without physically bursting apart. The vacuum weaponizes your own essential fluids, turning them into expanding gases that attack you from the inside out. Because you've emptied your lungs to save them, the blood flowing up into your skull is now completely starved of oxygen. By the 11-second mark, your brain runs out of oxygen and you lose consciousness entirely. Once the brain goes dark, your cardiovascular and nervous systems systematically shut down. While your internal organs are failing, your exposed skin is absorbing unfiltered cosmic radiation and rapidly shifting between extreme heat and deep cold. At 11 seconds, your mind has surrendered and your body is completely incapacitated. But biologically speaking, you are still alive. This timeline charts the limit of human survival. If rescue occurs within this highlighted window of 60 to 90 seconds, there's a chance. Survival depends on immediate recompression. The body must rapidly return to 1 atmosphere of pressure before the clock runs out. Medical science shows that if recompression happens in time, the astronaut has a high probability of waking up and making a full recovery, despite the severe trauma of boiling fluids and oxygen starvation. Those 90 seconds are a rigid test of our biological resilience in an environment entirely hostile to life. That fragile resilience is exactly why we rely on this impenetrable barrier. The spacesuit artificially negates the vacuum by supplying its own pressurized atmosphere, a constant stream of oxygen, and heavy shielding against cosmic radiation. It allows astronauts to ignore the fatal physics of ebullism, working smoothly while suspended in the deadliest environment known to science. A spacesuit is an individual, human-shaped spacecraft, serving as a wearable set of armor that brings the conditions of Earth out into the void.